So I will tell about some stability analysis. I will not do any analysis. Just I will tell that what could be the. Since yesterday also there was some discussion whether limit-equilibrium finite element method and all these things are there. Some salient features only are discussed. So this is a typical slurry. Dr. Ponda also not aware because this time we will not able to do it. So this is basically how we are doing, and there are now two types of there. Sometimes we also do it, high concentration slurry. So you will see very quickly it dries out, particularly ash pond, because some of the problems are asked with the ash pond. So this is typically what we follow in an ash dam. Because that is different, somewhat different from the tailing pond. So this is what we follow, and all these toe drains and all these tube drains. So this is an ideal one. So this is an ideal one, and I am next what I am showing what is typically how it has been constructed. Suppose say here also in the starter dike there might be a clay core for making it impermeable, and then what they are doing, they are providing the filters here. And similarly, this is somewhere now what some places are putting this water escape structures what we were saying yesterday. So here they are trying to store in between in the pond itself somewhere. So they want to put it in this way in the storage lagoon, and this recently somewhere in UP there is some problem because sometimes it creates a problem, and that is become difficult only because inside the pond they are putting it, accessibility and other things has become an issue. Okay, so this is because now recently it's a matter of concern. Now they are putting LDP or LDP liner here. They are putting the liners. Because what we are talking about, what is the role of this filter? Suppose, because Dr. Ponda was not talking about that, first you draw this phreatic line, then take this phreatic line and do the slope stability analysis. Because slope stability analysis mostly now the software is doing it. You have to simply put the inputs. But the more difficult part is that what should be the input? How to interpret that input and where I should get the input, that is more important, not doing the analysis. Because it has, I'll show you whether limiting or flaxis, I have to deal with both the things. The values are almost incoming. Factor of safety also you can get through flaxis. So flaxis will give you extra settlement and so on, but you can get both. But the problem is that making a schematic diagram or your project proposal in the sense what should my dike should look like, what are the features of the dike, what should the material properties of a dike. Because I saw also that example, it has happened once. That example when it comes, I will tell you. So that's why what we are doing. Now if I am putting a chimney here, this part becoming dry. So this part become dry, its strength will increase, but water pressure is not there. And so also you see, if I am putting a toe drain, that is the role of toe drain. So simply everything is diverting this water, making it an easy pass to pass through this. So this modeling this in Flaxis or GeoStudio, whatever the methods you are following, idea is that can you take this exact geometry with all these features in it. Suppose I am talking about this simple geometry. So they are different material. This part is dry, this part is somewhat or wet, saturated. So their property will be different. You cannot take the same property for both the cases. So then you will get different factor of safety. So also here. But as Dr. Pata said, we may take the worst case. If you want to, because we always say better to be safe than sorry. But this is what for which we can make it more stable. Okay, yesterday also some of the things that whether we will put the vegetation or not. This is some of the picture from some abandoned dikes. So already the trees are there, it has been grown up on the dike. But this is abandoned, not working anymore. So that is the question. Okay. So now you see, This is another for which suppose I will go for a slope stability analysis. Now I have got done a raging. So in this raging, first I have to make a diagram or make a geometrical model. So what is there in? So now what I have done, so like these are some of the case studies which suppose have been done and analyzed and found that it is working. So this is suppose this is the starter. So obviously yesterday there was some, always the starter dam is in earthen pond. And here in this case you see what we are doing. So these were initial, again also suppose say we are going with an earthen bond extension. This is another case what they found. Suppose this existing earthen bond is sufficient, so they have got a space, so they increase it. But where they increase, you see what they are doing. Suppose this is my water level. Water is coming. Here I am providing a drainage so that it goes out. So every arrangement, if you will see, they are trying to do it pass through the water. So this is here when we are going for a downstream raging, and here it is also. Suppose say I am raging first, which the existing after bond is not sufficient, I first raging, then I will go for the further raging with the fly ash. This is another central line raging. It is all happened in India only. So we are initial, now we are not going, but still we have some soap or somewhere it has been done already. So here it's there in. So what we will do, this is an ash deposit. Instead of, because these are very old, I mean 2010, 29, 2011, mostly that time also, we are getting it and using earthen also. So that time central line methods also, but one thing you see, here we are trying to make this phreatic line and passing through this. Where this pitching is there, so water we are trying to pass through this one, connecting from one to other. So here it is with, suppose say here it is writing, not written the earthen one, so it will fly ash. So here what is there in, suppose I am using fly ash. So in this case, and if you will see in this, they have also 1.5:1. I mean the slope is very steep in compared to what the tailing dam, what they are seeing 2.5 or 3. But these are all there because initially these fly ash dikes were simply designed as small embankments or dikes, because dams and dikes, so dikes obviously lost its importance in an water retaining structure also. So that was the name. So this is how, that is also with 1:1.5, and you see 1:1.5, everything is there, and this only the gravel pitching or the drainage layer has been connected. All other things 5 meter, this is the minimum 5 meter, 7.5 meter, all these things are as usual. Now what I will do, I will go with this one. This is the type of picture. So this picture or geometry, I am first envisaging that my dam will be looking like this. Like Dr. Panda said that we are doing all two-dimensional, and this geometry should be the most critical geometry. That this geometry where the slope is 1.5, suppose is critical, that 1.5. And suppose the maximum here the water table is going, so that's the section I have to consider. Because 3-dimensional altogether, yeah, dike managing in a computer software, people think it is not worth. So better to go with, it will be worth in the sense if you want to really save it, but there are some other uncertainty. So that's why people think that let's consider the worst section and do it. So far also we are everywhere doing this 2D analysis. So this is another example. So these analysis, just what I want to say, that all these analyses are somewhere it is connected, somewhere it is not connected. This also comes in problem. And suppose I am going for the raging. If somebody is already down the dam, I have no choice, because some of the things might not be there. I forgot to bring that picture maybe, because in one case that this slurry on which I am providing the dike is not sufficiently dry, or the strength was found to be less. In that case, people are putting now a stone column. PVD drains and stone columns. Stone columns also through which you can improve the bearing capacity of the soil. And when it comes to the dam, suppose in those days these dams were constructed not thinking about that what will be the height of the raising. Simply like one example we were discussing about, think about the unit weight of the tailing, like a red mud, 20 kilonewton per meter cube. If I make suppose say 20 meter high, so that becomes 400 kilonewton per meter square. Whether that soil can take that load or not, because simply I am multiplying with the unit weight. And think about suppose say we will go to how much height. If I go for 60 meter, so then what is the bearing capacity of 1200 kilonewton per meter square? When case of tailing pond, when it is built on the rock, that is not an issue. But the issue is particularly these arch dikes. Arch dikes are built on the plain terrains and many times in all the agricultural, all that type of land. So there we need to find out what is the bearing capacity, keeping in mind future expansion. Because if that dam is weak, so then there will be a control, because some exam problem was there, what should be the height of the dike? How much I can go for it? Because if I have not treated the foundation properly, even if you are, because slope stability comes the top slope or somewhere it will slip. But what about the bearing? So if the bearing capacity is not sufficient, whatever the measure, make it 1:3 or 1:3.5, but the overburden itself will not allow it to stand. So then there will be a vertical crack. That means that it will settle down and the crack will be there like this. So it is not like a slope failure, rather it will be a foundation failure. So that was the point when we were talking about clay soil. So that needs treatment. And there is one sentence in geotechnical engineering, the foundation can be built over butter. Butter is very soft. Even also there you can put the foundation provided to the treatment. So that's why many soft clays, many places are soft clays from Venice to Bangkok to Hong Kong, and say everywhere things have been done. But only thing you have to identify and rectify. So what Dr. Ponda was talking about, the stabilization and other things, we can do it. Again, so that aspect is one. First one I said bearing capacity, which is generally we didn't discuss suppose in slope stability, but that is also the criteria we need to try keep in mind. And many times suppose I am going to raise it, and now we have to make a borehole on the dike itself. Then sometimes they don't allow. So they say that we do in the pond. So Subhrasu can tell you, so do how they, because that is a 4-5 meter. Suppose a 30-40 meter original, because it has slope raised like this. Maybe suppose here I say. So here it is my, if I want to put it. This so if it is upstream side raising, so do they allow in the original embankment? They will not allow. So how you will know that what is there in? So only nowadays geophysical exploration through this MSW or so, you can get some information. Otherwise, most of the emphasis is on the pond itself, because just to check that the soil, what is the bearing capacity, how much it can take, and then on that, because on that I am putting it upstream method. But I am forgetting that this way. But fortunately, compared here, it may be, suppose it is not central method, the load may be less here. But I cannot ignore it, because if it is weak, this will, the pore pressure or this strength reduce, and that becomes a vulnerable point. And where we cannot find out information. In situ testing, even the cone penetration, when we cannot do it, that time we can go for geophysical exploration. So geophysical exploration non-invasive. It will not penetrate through it. So these are some of the aspects, finding out the parameter and so on. Now suppose I am going for analysis. So here I am talking about a particular slope. Here you see slope W. That geo slope W it is there in. So here I got factor of safety 0.97, similar type of slope. Suppose say here I am talking about one example, they did it limit-equilibrium method. Then there is a flag which is called finite difference method, that is numerical method. So they also have done some analysis, they have also get it. Now yesterday we were talking about the Plaxis. Plaxis can also do the analysis and also can find out factor of safety. So then finally now people are also using called discrete element method, which is very difficult to, to wait long to do this. They say also same company, they are Clark and this DL are same company, that Itasca. So they are some company. So there also you can, but there you have to write down some of your own code with his software keys, then only they can connect it. So there basically in these type of fine particles it is very difficult and it takes also lots of time to do analysis. So that's why what being like here, this is the most preliminary. Suppose you want to find out immediately what should the factor of safety, because in one trial, in a design there cannot be a single trial. That's why Dr. Ponda, I think day before yesterday you were showing, out of so many 20 or plus alternatives, so one alternative was best. So you cannot just do one alternative with this discrete element method after 7 days. So then it is not there. So if you want to do it, you do with 20 experiment with the limit equilibrium method, find out which is coming better. If you want to verify it, then you can take one model and using discrete method. So because this, when I am talking about FLAC and Plaxis, still we can manage, but DEM is still difficult. Difficult in the sense time consuming, modeling also difficult. So needs skilled thing. So this is one aspect. Now, in that waste containment system, here I talked it, this is long before in 2010. It has failed because failure gives the idea that this is in USA. Okay, most of the things you say, not USA, both all North America, South America, and Europe, everywhere it is there in. So I collected data from US website, and so you see, it has failed. Where it has failed, most of the time are the liner, when it is a translational failure. Particularly these are not tailing containment, these are this municipal solid waste containment system. So failure can be different, a single rotational, a multi-rotational, translational, and so on. That means first, the basic concept is that, or this limit equilibrium method, when I am talking about this limit equilibrium method, it assumes a typical failure surface like this. So where it should, if suppose it gives a rotational type of failure, so is it the appropriate failure? As per your EVA provided, suppose it is sliding through SDP liner. So it is not a rotational, it will be just a sliding translational failure. So that aspect also we need to keep it, that you see, when I put the geomembrane, all are translational failure. Because this has been observed when all this waste containment, actually this as I made it clear, it is not the tailing, but they say waste containment. So that means when we are talking about this geomembrane also.
What is the translational and rotational failure?
Translational means here I am talking about, this is a rotational failure. It fails like a, you see the slide will slope fail like this, slope. You see it is a slope fails like this, slide cutter.
Right, sir.
Translational means, I will show the diagram, this one. Just like along this line it is sliding. Already there is a predefined line, along that it is just sliding.
Okay.
Because that is SDP. SDP liner that what you are providing, okay. Because that SDP are what is there in, because it is a separating layer.
Correct.
So sometimes also, so then only it has been revealed. This is old 2010 I am talking about the information. Now they have done it, and now how to get it. Particularly in the waste containment, this SDP liner is more important. Impermeability is more important there. Then they consider also the slope stability. So while considering in the countries like US also, so many failure has happened, and Europe also. Okay, so this is where, so we have to find out, so that the judgment before going to modeling, these are the things we have to keep in mind. And in general, it will go for a slope stability. These are so many factors which is affecting, because yesterday we were talking about seismic activity, that is dynamic force. And in suppose in these coal mine cases, this blasting also comes into effect, or any mining area, or in other cases like where we have got that is limestone and other things. There also sometimes that also became issue. So blasting is also issue and seismic is there. Next, what is the method we are following? Many a times during operation it has failed, because that also depends upon this equipment or gadget, particularly in coal mine. So during operation many times the dump has stopped, collapsed. So then strength, so many factors of the strength or the parameters are there in, and then the groundwater. So in the groundwater also you can say, so there are different factors which is there in, that also need to consider, and then foundation strength. So this will depend upon particularly when I'm talking spoil, that means the dump, that rock, waste rock, and then the geometry. This zonation is where suppose I am putting a HDP liner that makes a zone, or naturally that could be also a zone. If suppose say we are putting on the ground.
Sir, how to counter this translational failure? If we are using the HDP liner over there, then the slope is become the stability. That's the, you said that we can do the slope strengthening or something like that. How to counter that translation?
Okay, there are strengthening are different ways.
Okay.
Here first I said when I was talking about him, so I tried to answer him about the enforcing the foundation, that is first pillar. Similarly, we can do also strengthening of the slope. But when we are talking about strengthening, that we do when there is an existing natural slope. But here I have to revise my design to take care of it. And in general, by default, we do benching. Or we do, suppose say, zigzag benching, that I can say benching. So that is the way we can do to avoid these translational slides. Okay, I'll come to that. Now think about, so these are the factors which is affecting. Now the judgment is that what these conditions are there before sitting on front of the computer to put the values. Okay, by default we defined as a infinite slope failure or finite slope failure. So theoretically there are two types of failure. It is infinite or finite. It is not that infinite, finite, the name has been there in. So if you see, this is like as we are dumping from the truck, it is taking its own slope in a granular soil, so it is like an infinite slope. The granular soil, it will slide as a long way. But the clay soil, very shallow failure. In embankment you see small failure, even at near the toe it will slide and stay here. But suppose in hilly terrain with dry, sandy or coarse grain material, it will slide a long distance but the depth is less. So that is called infinite and finite slope failure. According the analysis also becomes different, and then mostly infinite you will see it is like a translation, just slides down there on that. The shallow depth. So now, so this is also, these are all, because in slope stability, this is a born. You see, yesterday the very first or second we were talking about how this born is going to help. If you provide a born, how it is going to help the stability of the slope. So this helps. What we are trying to do, when it tries to slide and go out, this is giving an obstruction. So it will give it try to protect. What is happening? All this trying to slide out. When it is trying to slide out, this born will help to stop it. So that is the use of a born. So if I need, or if I found, no, whatever the slope it is not sufficient, I will provide a born, then my geometry will change only. So this geometry, making a geometry, appropriate geometry, that also may be, and all these parameters, out of this, only sometimes this may be constant binding, otherwise these, with these only I can play height and particularly slope, if height is fixed also. So that I try to use it. If not so, then I made the modification in other places. Okay. So this limit equilibrium method, I say Flyknit method. So there are so many methods are there. If you will see, if you will go to a software, there are so many methods. And now mostly Geoslope is using which one? Core of engineer. All in there. All are there. Okay. So that means, so which method will go for? For me, actually, whatever, mostly there is a called Bishop's simplified method. Bishop's simplified method. Suppose it depends upon. So we somewhere we get confidence with Bishop's simplified method. But all these methods are there. So that will also give you a different, maybe a different value. Somewhere this Sharma's method also. Geoslope or Stable में Sharma.
This Morgenstern and Price is the latest
version.
And that's a good method also.
Yes. Morgenstern, actually you are talking about PK Morgenstern, he is already 90 plus. So this method is 70s, not now. And Morgenstern is geotechnical, Price is computer science.
But it is coming very soon, it will be all numerical.
Yes. So,
But sir, by choosing this different method, the software gives the different factor of safety?
Yes.
Oh my goodness.
Yes.
so you have to go the minimum.
Minimum.
Yes.
So, like person who does the analysis, he has to follow, he has to choose all the methods and check the factor of safety for all the methods and go for the minimum. Is it like
Yes,
that?
that is, yes please, you are.
I understand that because I have done like thousands of this kind of things. So every method has some assumptions. So we have to see like in our case, in our
site, which is appropriate, like which gives their assumptions, because each one has assumptions. Like we are saying, translational. Like translational needs like a critical test, like which is the like liner. We are putting the liner in the slope. Definitely we are causing. That's the like I mentioned to you. Identify the weak zones. The liner is the weak zones. So that's why there are some methods which will treat that better. But if you are completely homogeneous soil, Bishop is the best.
Okay.
But that doesn't exist in nature.
That doesn't exist.
I mean homogeneous soil, it is very
It
difficult.
doesn't exist. It's for theory. It says like soil is homogeneous, it's like
Isotrophic.
And all this.
it doesn't exist.
So like I found Bishop's is very easy in MS Excel also you can do it. That's why. So that way, and that is gives initially 10 to 20% error may that is acceptable.
And it gives the minimum factor of safety, sir.
You have to obviously use the minimum
Minimum factor.
factor.
So Bishops gives minimum factor?
No.
It is not like that.
Bishop's gives quickly initially when the computer was not advanced. Morgenstern Price was taking time because as I said, Morgenstern is civil engineer, but Price is the computer science engineer.
Okay.
So those days computer was so weak, so they combinedly developed that software.
Even coming to the minimum factor of safety, again we have also like this source method. The source method we find which is the critical. Critical means which gives you the minimum factor of safety. But in general, if we see in theory, how we calculate it. In theory, we assume like there is a failure plan. So that's what also we recommend. Like I always recommend who does the limit equilibrium model that he should know what should be the failure surface. Because if you have no idea, then we are totally depending on the software. Because software is telling us this is my failure surface. But again, we always do like software to find the failure surface, but we see that and make sure that's realistic.
Yes.
So,
Because
can you give us some example?
I am showing that example. I'll go show him some example.
There will be some example.
I also make example. Because you will see, now you will see limit equilibrium. What we are assuming? We are assuming a circular surface. All these methods, a particular slope. the particular side means that slide. So particular slope I am considering, so I am applying, but is that slope is the minimum factor safety? So I have to take 100 trials, maybe 200, but now the software what is doing, it is searching. That's why he said there is a search method. I am showing that one of the search method, because this is mathematically, it's a non-linear equation. That means you have a multiple values. So that way we will get the minimum. That for that is called optimization techniques in mathematics. So that we use, and then we do analysis to find out the minimum. So we make an increment. Suppose I look at this one. I just missed that part. Suppose what is this circular surface? So its circular surface or suppose a geometry might be a center here and this is the radius. Now next what I will do, I will try a circle here, whose center will be here and radius may be different. But the computer also in software tabular, so they also range. Give this range of R value and this position of the center, then they will start searching to make you easier. If you don't give, they will search randomly and it may take time. So that is the advantage of using again software, because if I do with MS Excel, at a time I will take one circle and analyze. Again I will change the center, radius, another circle.
Sir, whether it is the computer or us, what is the basis of searching these sleep circuits?
Searching means where we will get the minimum factor of safety. Because what happens? Okay, what is factor of safety? Factor of safety is equal to your moment of disturbances or resistance. Moment of force. That moment of disturbance and moment of resistance. Who is disturbing? The self-weight is trying to make it slide. The self-weight, or if you are putting any load of the truck, vehicle or whatever it may be. So they are trying to make it slide. And who is resisting? The strength of the soil.
Friction.
Friction. And friction is the unit is suppose a kilometer square. So what is the size about which it is traveling? I mean the area. Because I am taking only a single slice, 1 meter I am thinking. So how much is this length? This length is more, resistance is more. This distance or length is less, the resistance is less. So my circle, if you see this part, this is also important. This part.
Length of arc.
This length of the arc. So that part is the resistance. So strength multiply this aspect. So if I can take it deeper, wider, so then the factor of safety will increase. Because the keeping that weight, because in the slope here, now only in embankment, now we are considering certain weight, 1 kilometer square, 2 kilometer square as the vehicle load. Otherwise, most of the time we assume like this is self weight and we are analyzing. On this, it should be able to stable. And particularly in the arch dikes or these tailing dams. So now when this moment of resistance to be increased, so that depends upon the sliding plane. This sliding plane, how much is it, how it is.
This only occurs on downstream side slope.
No, both sides you have to check it. You see, particularly in the slope stability, when it was used in 1920-30s, that was costly for the water dams, I mean water retaining dams. Because that time nothing was there in embankment was also they were able to manage. But when they started creating dam, that time there was a requirement of the slope stability. That is first called ordinary method of slice or Fellinius method. All this started in that time when they wanted to analyze a dam. So dam, the critical condition is that drawdown case. Suddenly, suppose say what you do, allow this water to pass through, that time the dam fails. So that the condition will be different, so you have to check the different condition. But in tailing the case is different. Embankment the case is different. That sudden drawdown means suppose a filled with water and you open all the gates and that is in a quickly allow it. So if it there, suddenly that slope will fail. So that is so typical critical case will depend upon the type of embankment.
And that will be upstream failure. Southern downtown is upstream failure.
Obviously.
Because it was pressurized at the beginning and
Then that happens, so that means a pore water facility and so many other things are there. So that is what we need to check. What is my embankment is. Slope stability everywhere, natural soil is there also in embankment. So accordingly the critical situation will be different. So I cannot tell the computer to do all sorts of analysis. I should have my judgment. Which methods I should put it here.
So, like I can add one thing. We start with the starter dam. Starter dam we do both, upstream, downstream. But as we go on raising, we know that this upstream is now no longer available. So we sweep everything to downstream. And in the downstream, like say we give the salts. So in the salts, you will provide salts in the both, like in the crest and in the toe. Give better distance. Like the computer go and do like 2,000, we generate 8,000, 10,000, depending on like what satisfies you. So then it will come up with this is my minimum slip circle. This is the slip circle which has the minimum approximate. So you look at that slip circle and make a decision there. Is that realistic? Okay? That decision depends on the engineer who is knowledgeable on that type. Other people can, like again, experienced people, when we see that, we know that what it looks like, but you have to make a decision. Yes, this slip circle, which is program is telling me no, is okay. If you think it's not okay, then you change your search method to find the one which you think is okay. Because any slip circle very close to the face, there will be some generator very close to the face, that can fail, but that will give you minimum, but that doesn't.
Local failure.
Local
failure.
You see? So decision is yours. You have to make that decision. That's why I make that sentence like whoever is doing using the model should already know that my failure surface will be that. Don't depend on that computer is telling me.
And most of the drawings I found, the slip circle begins at the top and it ends at the toe.
That's the idea. Because it's not that it is a full scale, it is failing. A small local failure, we are ignoring it. We want to see that whole dam is failing. That is the main thing we want to protect. There always will be some very small failure. Like if you go ahead and in that one, there was along the toe, there was also a small slope.
You see, suppose it fails like this.
In design they are not considering like this.
No. They are design. Suppose a computer panel gives this is a failure. So that time is a local failure. It's not a problem. But suppose this is a, here itself there may be matter of concern. So here it suppose it fails. And what you are saying, everything comes, this is called toe. Why it is toe? Because if you assume this is my rigid, good strength. So the failure surface starts from here, it is coming. Okay? But it is hard. It is not able to pass through this. What is doing? It is going here once.
Most of these results are like
because we are assuming that is very strong. If I give that soil as weak, it will also pass through that. That is called base failure. There are different types of failure. Base failure, slope failure, toe failure.
base failure, foundation failure.
Yeah. So, if we are raising, like I showed you that big dam raising, so we also we see also the lower level failure and also middle failure and also whole thing failure. We also look into 3 different aspects and make sure everything is good.